Hey guys, welcome back. In this video, what we're going to talk about again is the central limit theorem. We'll call this part 3, but we're going to look at how the central limit theorem applies to a proportion instead of a mean. All right, so what I have here is the central limit theorem restated again, just to kind of remind you of what it said. In general, what it had said before was that if we took samples of large enough sizes over and over and over again, and we distributed the means, or in this case, the proportions, right? That's what we're going to talk about today. If we took samples that were large enough, we could build a distribution that is normally distributed. All right, so a lot of the same stuff applies here with what we're going to see. We're gonna need sample sizes that are larger than 30. That's what it means to be sufficiently large. And the sampling distribution that we're going to use today is not going to be a sampling distribution of the mean like it was before. It's going to be a sampling distribution of the proportion. All right, so let's see a demonstration of that. All right, so we got this thing again where we're gonna run a simulation and we're gonna talk about what a proportion is and what happens to the distribution as we increase that sample size. All right, so to experiment with this, I'm going to, in my open math, right here, we're gonna go back to this sampling distributions simulation. So I'm gonna open that up. It takes me back to this page and you'll see sampling distributions here. Instead of the mean, we're gonna do proportions. Okay. And we're going to work with the first option that they give us here called college graduates. All right. And you'll notice over here they tell us about the original population. All right. And this population, what it's telling us is what is the proportion of all people. I'm assuming in the United States, but we'll say the proportion of all people that have a college degree or have graduated from college. And what they're telling us is in the population, the proportion of people that have graduated from college is 0.275, right? So in other words, if I were to go and select somebody at random and ask them if they had a college degree, there would be about a 27.5% chance that they did, all right? So that's what a proportion is. So we're not dealing with a mean. We're not taking an average. We're looking at a proportion, all right? What percentage of people meet some requirement or have some characteristic. So it's a binomial situation. It's a yes or a no question. Are you a college graduate? Yes or no. There's only two outcomes there, all right? So that's what we're dealing with. So this is a little bit different than the mean, right? So if you were to click on edit data here, you're not going to see anything because it would just be an assortment of yeses and nos. So what we're going to do, we'll just kind of start off here. I want to kind of talk about like some different sample sizes. Let's start off with a sample size of 1, okay? And we'll generate a sample. So this is the situation I was talking about. Like if we were just to go and pick one person at random and ask them if they were a college graduate, they would say yes or no. So let's do that. We'll generate one sample. There we go. And we can see what happened over here. So I asked one person if they were a college graduate. They said no, because I got one person, or I got 0 people that were a college graduate out of the one person that I sampled, which means the proportion there is 0, right? 0 out of 1 is 0. So the proportion is 0, and we would plot that on our dot plot over here. So we get that dot at 0. I generate another sample. And the second person, right? You can see my second dot right here, it appears, and that person also was not a college graduate, so the proportion in that sample was 0, right? And I can do this again. Oh, look, the third person that I sampled was a college graduate, right? So we got 1 out of 1, which is a proportion of 1, right? So we see the only dots that we're going to end up plotting here are either on 0 or 1 when we have a sample size of 1, right? Because like I said, it's either a yes or a no. There's only 2 outcomes for this one, all right? So if I were to generate like 1,000 of these, and you can kind of see like here's this real thick line right on 0 of all the people who were not college graduates, and these were all the ones that were, okay? And you'll notice like the distribution shape here, there's no name for it. I mean, this isn't skew or normal or anything. This is just a weird looking distribution with no shape whatsoever. All right, so now we're going to increase the sample size. So instead of asking just one person, I'm going to ask 10 people if they were college graduates, and I'm going to count how many of them were. All right, so let's generate one sample of size 10 and see what happens. There we go. So I sampled 10 people. 2 of them were college graduates, which gives me a proportion of 0.2. Right, so then I would plot that dot, and this begins my distribution. I do it again, and I got the exact same thing. So I got 2 again, so my second dot goes on 2. Do it again. Man, all right, so third one also got 2. I'm trying to get something different here so we can see what happens here. So I'm going to generate another one. Good Lord. All right. And again, oh my gosh, there we go. All right, so we generated 6 samples so far. And finally on the 6th sample, I got something different. I sampled 10 people. I got 3 of them being college graduates for a proportion of 0.3. So I put that dot right there. And you start to see a distribution building. Okay, so I'm going to generate a whole bunch of those samples now. Instead of just doing one at a time, generate maybe 10 at a time, right? And we start to see this distribution shape forming. And I bet you can guess what this shape is going to kind of look like here. Let's generate 100 of them, right? And we'll get up there, and then let's start generating thousands, right? Thousands of samples, because the central limit theorem says if we take these samples over and over again infinitely, we'll start to see that shape. Right, I'm going to go to 10,000 like we did in the previous examples. There we go. So now we're at 11,446 samples. Ooh, 13,000. I must have hit it a few more times. Right, and we start to see a shape, and it's not quite normal. Right, it's looks like it's skew right. It's got a longer tail over here on the right. The height or the max over here seems to be pushed off to the left a little bit. So this is definitely a skew right, which we expect, right? Because the sample sizes were only 10. They weren't sufficiently large. They weren't at 30. So I wasn't really expecting to see something that was perfectly normal, but it's pretty close. But it does have a slight skew, right? And notice that they've calculated the mean of all of those proportions that we found and the standard deviation of all those proportions that we found. So let's go put some of this into our notes. All right, so remember for the population, the proportion, and notice the notation here. This is the symbol that we use for population proportion. It's just it's a p, right? So I'm going to put a 0.275. Okay, so that's my population proportion. And when we did samples of size 10, we got a distribution that was skew right. All right, so we got something that kind of look like that, and I'm going to write down that shape. Okay, and it was slightly skewed right. It wasn't horribly skewed right. Okay, and then the mean that we got, and again, notice the notation change here. This is the mean of the sample proportions. All right, so it's a mean of those proportions that we found. All right, and notice the little symbol that they put above the p. And that is because now that comes from a sample and not the population, right? So these proportions came from all those samples of 10 that we took, and we found the average or the mean of those proportions, all right? And what we found was the average of those proportions was 0.278. I'm going to write that down here, 0.278. And then our standard deviation was 0.142. And I'll write that down. Okay. And again, this is the standard deviation of the sample proportion. So again, pay very close attention to that notation. That's going to be important when you go to read the homework problems and the quiz and the tests and stuff. You got to pay attention to that notation. There's a difference between this thing and these things, okay? So, all right, so here we go. Let's go and do what the central limit theorem says to do here. Let's pump up that sample size to 30, see if we get something that's normal, right? So I'm going to go back to my simulation here. I'm going to change this to 30, and it should reset the plot for me, and it does. All right, so I'm going to generate one sample. Boom. All right, so we asked 30 people if they were college graduates. 10 said yes. So 10 out of 30 is a proportion of 0.333, right? So we plotted dot. That gives us the first dot of our distribution. If I generate another one, right? This time 5 out of 30 people said yes. So we got a proportion of 0.167. There's our second dot. That's how this distribution is being built, right? So we're going to start generating them faster. Maybe do 10 at a time this time. Let's do 100 at a time. All right, and we start to see the shape form, and I'm going to generate thousands at a time. I'm going to get a whole bunch of them until I get up to about 10,000 or so. There we go. And we see that shape. And this is exactly what we expected to happen. Those sample sizes are now sufficiently large. The central limit theorem says when that happens, we're going to get a normal distribution, which we do. This is a perfect normal distribution. We have a mean, we have a standard deviation. Let's go put that in our notes here. Draw nice normal distribution. And I'm going to put in the mean that we found, which I believe was 0.274. Okay, and our standard deviation was 0.081. Okay, and here we go. All right, so our mean, right, the mean of all those proportions would be here in the middle, right? So this is where we would put the mean of the sampling distribution, and then same thing here. Right? That mean would be the middle of our distribution. Okay, and let's make some observations here, right? So we talk about the shape, right? As that sample size increased, we got more normal, right? So we got approximately normal here at the end as we increase that sample size. Look at the mean of the proportions, right? The population proportion was 0.275. The mean of the proportions from our sampling distribution was 0.278. Not a whole lot of difference. And even when I increased it to 30, it's at 0.274. So it did not change, right? So the mean of the sampling proportion is going to be equal to the population proportion. That is going to happen every single time, right? Now, the standard deviation that we see here, you'll notice that it does get smaller. When I had it at 10, we had a standard deviation of 0.142, but when I increased it to 30, it reduced quite a bit down to 0.081. And yes, there is a formula to help us calculate this thing so we don't have to run a simulation. And here is that formula, and I'll demonstrate it working here. It is the square root of P. Right, that's our population proportion. And I can write that a little neater. So let's see. Still trying to get used to this pen. Right, so we take P times 1 minus P over N. And all of this goes into the square root. And again, please excuse my poor handwriting here, but this is how we would calculate this standard deviation if we didn't want to have to, run the simulation over and over and over again like we just did. On that website. Okay, so sometimes they'll give us information, and really the only thing that we need to know is the population proportion and the sample size. So as long as they give us that information we're dealing with, we can calculate what the sampling distribution standard deviation is going to be. All right, so let's give that a try real quick. I'm gonna bring up my calculator here, and we're gonna see if we can calculate this thing, see if we get something close to 0.142. There we go. All right, so P, that's this thing right here, 0.275. Now let me get my square root going. So we got 0.275. Actually, I'll do the square root at the end. 0.275. And then in parentheses, we're going to do 1 minus 0.275. And I'm going to go ahead and hit enter. Right, so that's the top of that fraction. I'm going to divide by the sample size, which was 10. All right, so that's what would be in this number would be the number inside of the square root. So now I just got to square root that. I'm going to say square root of 0.0199 is 0.141, and that's really close to what we got here. So you can see that calculation works. I'm going to do it one more time, this time with the sample size of 30, and make sure that we get something close to 0.081. All right, so we got, again, it's going to be the same thing, right? It's going to be, and I'll just actually go up and grab it. So I can go up here. I can take this and divide it this time by 30 because our sample size is 30. And then I can square root that number. And there we go, we got 0.081, there it is. So almost a perfect match there. And we see that the calculation does work for us, so we don't have to do that simulation over and over again. Okay, So again, just to kind of summarize, right, for a proportion, it normalizes as we get to 30, as we get sufficiently large. The proportion of the population stays the same through the sampling distributions, and the standard deviation is going to decrease according to this formula right here. All right. So let's look at some problems that we might run into that might use this. All right. So we have to recognize situations that are proportions instead of means. All right. So first problem here. So this is, we're going back to Hawaii. If you remember those problems from the previous sets of notes. Okay, so we're back in Hawaii, and this time the University of Hawaii has decided to set a cutoff score on the SAT for admissions at 1300. That means to get accepted into this university, you need to get a score of a 1300 on the SAT. So then they looked at the population. Instead of all the juniors in the state who took the test, who took the SAT, only 18% of them got higher than a 1300 and 82% did not. All right, so this number that they're giving you here, this 18%, that's P. That's our population proportion. All right, this 82% they're giving you here, that's 1 minus P. That's your complement. Okay, now keep reading here. It says if 30 students, right? So sample, this is our sample size. This is N, right? So if we had 30 students apply to the University of Hawaii, we want to know the probability that 30% or more of them will have passed the SAT cutoff score. All right. So remember, we have sample sizes of 30. So if we imagine what our distribution is going to look like here, right, we're going to have a normal distribution because the sample size is sufficiently large according to the central limit theorem. The center of this thing, right, is going to be 0.18. Remember, the population proportion is the same as the mean of the sampling distribution. Okay, so that 0.18 is going to end up in the middle. That is our mean of all the proportions of size 30. Okay, now remember what we want. We want to know the probability that 30% or more of them will pass. So 30% is 0.3, right, which let's say is over here. So here's 0.3. This is our cutoff, right, or our left bound, and we want to find the probability that 30% or more will pass. We want all of this area underneath the curve here. All right, it is normal, so we can use a normal CDF to calculate that area. So I'm going to go ahead and set that up. Start with a normal CDF. Our left bound is 0.3. Our right bound is going to be infinity, so we're going to put in a 1E99. And then we need the mean of the sampling distribution, right? So we need the mean of the proportions, the mean of the sample proportions, which we know is the same as the population proportion, so that's 0.18. I'm going to go ahead and put my 0.18 in there. And then we need the standard deviation of the population proportion. So we've got to take 0.18 times 1 minus 0.18. We have to divide by 30. And then we have to square root that thing, right? So we have to calculate this. Let's see what we get. I'm going to go to my calculator and see how that works out. So we got 0.18 times 1 minus 0.18. There it is. I'm going to divide by 30. And then I'm going to square root. Then we got 0.07. All right, so we'll say 0.07 is the standard deviation of the sample proportions. So I'm going to put a 0.07 in here for the last piece of my normal CDF. And I'm going to go back to my calculator and crunch that number. So let's see what we get. Oops. There we go. So we got a second distribution, normal CDF, which is option 2. And we're going to say 0.3 for our lower bound. We're going to say 1E99. For the upper bound, we've got 0.18 for the mean, and we've got a 0.07 the standard deviation. Let's see what our probability is going to be here. We've got 0.043. that is our, there we go. So there's our probability that we're looking for. Okay. Again, most common mistakes students will make, they will just, they'll get lost on the standard deviation there. So make sure, like, think about the things that you need for this normal CDF. You need your lower, your upper, and you need your mean and your standard deviation. Like, you got to find all of those things. Students tend to get messed up here with finding that standard deviation. Okay. The other thing they get confused with, I'll see a lot of them use the standard deviation calculation for means instead of proportions because they forget that this is a proportion problem. All right, let's go to the next one. Let's do it one more time. Okay, and let's make sure we pick out the important information here. So again, same thing. They have a cutoff score of 1,300. The juniors in the state took the test. It's still 18%. So we have P. Right, and here we have 1 minus P, so we got those two pieces of information. This time the sample size is 100, right, so it says if 100 students apply, what is the probability that between 30 and 50% will pass? So this is like our upper and lower bound when we get to the normal distribution. All right, so let's start with that. Is it going to be normal? Yes, the sample size is sufficiently large. So I'm going to draw my normal distribution. There it is. What number am I going to put here? If you said 0.18, it did good, right? Because remember the population proportion is also the mean of the sample proportions, all right? And then we want between 30 and 50%, right? So 30, let's say, is right here. Let's say 0.3 is right here. 0.5 is somewhere over here. And we want this area underneath the curve in between those two values. Okay, and we want to make sure that we note the mean of the sampling distribution, so the mean of the proportions, and the standard deviation of the proportions as well. We should probably go ahead and just calculate those now because we know we're going to need them. All right, so remember the mean of the proportions was 0.18. That doesn't change. And then this one, we're going to take that 0.18, multiply it by 1 minus 0.18. We're going to divide by the sample size, which in this case is 100. And then we're going to square root. There we go. All right, let's go to our calculator, run that calculation real quick. So I'll clear out some of this old stuff. So we got 0.18, 1 minus 0.18, enter, divided by 100, and square root. And there we go. So we got a 0.038. All right, I think we got everything we need. So it is normal. So I'll set up a normal CDF. There we go. Lower bound, 0.3. Upper bound, 0.5. And our mean, 0.18. And our standard deviation, 0.038. And let's run that calculation real quick. We got vars, option 2, and okay, we got the lower in there at 0.3. That's good. We're going to stop it at 0.5 this time. Mean is good, and the standard deviation is going to be 0.038. And enter. Okay, so we got a 0 plus. 7.946. So remember, this is an E-4. So if I were rounding to 4 decimal places, all right, this would actually be 0.0007. Okay. You're more than welcome to write 0 plus, but in MyOpenMath, if they say to round to 4 decimal places and you get an E-4, that very first number is going to be the 4th decimal place. Okay, so I should probably round that up because if I look at the next one, it's a 9. I should probably round that up to 8 to get MyOpenMath to consider that correct. Okay, and speaking of MyOpenMath, these problems that I just did, that I just demonstrated for you, these are going to be very helpful for problem 8 and problem 9 in your homework set. Okay, so make sure you review this first, then try those problems for 8 and 9, see how you do. All right, if you get it wrong, make sure you look at the solutions, hit show solutions and read through those, watch this video again, and then just click on try another similar problem and try again. All right, don't give up on them. And of course, if you have questions, as always, you can go to the forum, post your questions, or send me a message and I'll try and answer them for you. All right, good luck.